So number 11 says distinguish between polar and nonpolar molecules. Well, there's two conditions that are true for all polar molecules. What has to be true about their bonds? They have to be polar. Yeah, they have to be between different atoms. If you don't have polar bonds, or you have a positive and negative end to your atom, no. Polar bonds can create polar molecules, but they don't always. So one condition is it must have polar bonds. By it, I mean the molecule. And if it has polar bonds, molecule must have a shape that results in a positive end and a negative end. So what kind of shape would that be? It would be what we call asymmetrical. What makes it asymmetrical? Lone pair on the center atom. Okay, so the first condition is that they have polar bonds. If they have polar bonds, then you have to look at the shape and see if the shape is going to allow for a positive end and a negative end to result. Yeah. Not the bond, the molecule. What makes the shape asymmetrical? We'll look at that. Okay, I'll draw an example of those. So let me just put nonpolar molecules either have nonpolar bonds with any shape, molecular shape, or they have polar bonds with a symmetrical shape. So I've got O3 here and Ch8 and I'll add a couple others here, but these are two molecules we've looked at a couple times tonight. O3, remember, has a bent or V shape. But what's true about the bonds in O3? Are they polar or nonpolar? They're nonpolar because they're all between oxygen. So it doesn't matter if it's a double or triple bond. Oxygen, whether it's forming a double bond with itself or a single bond with itself, oxygen has the same attraction. Every oxygen atom does. So it's got nonpolar molecules or nonpolar bonds. So this has to be a nonpolar molecule. CHO you could still, yeah, then the shape doesn't matter. So as soon as you know it's a nonpolar bond, you know the molecule's nonpolar. You don't even have to worry about the shape. Because remember, polarity means a positive end and a negative end, and that's caused by having a polar bond. The unequal sharing is what gives you a positive and negative end. So if you don't have a polar bond, if you have equal sharing, then the shape doesn't matter. If I have CH2O, this one, you know what, let me change that example. Let me give you a couple of different examples so we cover a little of everything. Okay, so I want to look at H2O, BH3, NO3, the other three shapes that we're familiar with that we did in our lab. So H2O, if you remember, bonds with a single bond between each hydrogen and the oxygen, but then the oxygen has two lone pair. So polar or nonpolar bonds? polar because it's hydrogen and oxygen. In fact, these are really polar bonds. Oxygen has the electrons more of the time, so oxygen has more of a negative end to it. Hydrogen's more positive. What's the shape of water? It's bent. Those two lone pair bend it. In fact, sometimes it's called double bent because it gets pushed down by two lone pair instead of just one. So now that I've got a bent molecule, these two hydrogen push down to one side. Up here, the lone pairs are taking up that space. So now I have a positive end and a negative end. This end by the oxygen, pretty strongly negative because there's two polar bonds with the electrons hanging out there. You got 4 extra electrons hanging out there. Hydrogen, those two hydrogen most of the time don't have any electrons by them. All that's there is its nucleus, its proton. So this is definitely a polar molecule. In fact, water is one of the more polar molecules out there. Definite positive end, definite negative end. BH3, on the other hand, the 3 hydrogen bond on. Boron is the other one that's too small to make a double bond, plus hydrogen's too small to make a double bond. So this is all you get for BH3. You just have this incomplete octet. Polar or nonpolar bonds? Polar. What's the shape? Trigonal, planar, because I don't have any lone pairs messing up my triangle. Boron and hydrogen, hydrogen's more electronegative, so those ends are going to be negatively charged. The boron's going to pick up more of a positive charge. Is there a positive end and negative end to this molecule? No, it's symmetrical. Those 3 hydrogens are perfectly spaced around the boron. So no lone pairs on the center atom, no polarity. Yeah. In this case, yes. My boron's going to have more of a positive end to it because the electrons don't hang out by the boron as much. It's not as strong as hydrogen. Hydrogen's more electronegative. I'm pretty sure. I'll double check that on a chart. Oxygen, that center atom becomes very negative because it hangs on to the electrons more of the time. NO3 minus, this one bonds with one double bond. No, it doesn't. Let me think about this. 5, 6, 24. Yeah, it does have one double bond. This isn't the one I want. Okay, let me pause and think of a different example. I want something that's trigonal pyramidal. Okay, let's go with PO3 minus 3. I don't know, I lost my minus 3 there, but I did. Oh no, that's not what I want either. Okay, let's go with NH3. So NH3, when it bonds, just makes a single bond with each hydrogen. And then it needs a lone pair on that nitrogen. So still have polar bonds. But now my shape, instead of being trigonal planar, these 3 hydrogen get pushed closer together. In fact, if I drew this a little more 3-dimensional, you'd see these 3 hydrogen pushed down, kind of in a triangle below it. So this is trigonal pyramidal is what it's called. Again, you have your chart to figure out these shapes. But because I have a lone pair, nitrogen's more electronegative, so the electrons from each of these pairs are going to be pulled closer to the nitrogen. So that makes the nitrogen negative, makes these hydrogen positive. And because of that lone pair, I have a definite negative end and positive end to my molecule. So this is a polar molecule. The one final example I have for you, this is a question I think it was Isaac brought up, was if you have carbon single bonded to 2 hydrogen, double bonded to this oxygen, This is trigonal planar, so it looks like it should be a nonpolar molecule. Looks a lot like our BH3, polar bonds, but a trigonal planar. But this one's a weird case because oxygen can pull these electrons closer to it, so the oxygen's negative, leaving this part of the carbon positive. But carbon can pull the electrons closer to it than the hydrogen can. So because I don't have the same things attached to the carbon, this is a symmetrical molecule that's actually going to be a polar molecule. That's not one you're expected to know. I just brought that up because somebody asked about it. But yes, if you don't have the same things around it, that also will throw it out of balance. Think of it like being a tug of war. If you don't have, the same amount of pull from all three atoms, it's going to affect things.